We'll now get into a very brief overview of several different data structures that we can use in our programs. And specifically, we're going to be looking at the strengths and the weaknesses of these different data structures. Whenever we write a program, one of the most important decisions, or a key decision that we make, is what data structure do we use to represent our data? Do we use an array? Do we use a linked list? Do we use a stack? Do we use a queue, and so forth? So we're going to take a look at several of those data structures, and specifically we'll look at the strengths and weaknesses of some of the major data structures. We're not going to be able to go through all of them in this class, but we can at least give an overview of the most common ones that we would use. Now, with that said, I should mention that there will be some data structures I mentioned here that we will not actually get into in this class. Some of these will actually be discussed in other classes, such as our CS 201 data structures course. Let's start with the array data structure that we talked about in CS 121. So we'll look at the advantages first. So one of the first advantages is that insertion is very quick. Now, what we mean by this is that we can add something to the end. So we will talk about later on how we can add more elements to the end of a fixed size array, but we can insert stuff very quickly. Another advantage is if we know the index of a particular element, then we can directly access that element. So we have fast access if we know that particular index. Now, there are some disadvantages with this data structure as well. One of them is that searching is slow. So if we're going to find a particular element, well, it takes a while to search for it. So we might have to search for the entire thing. Deleting an element of the array is also very slow, because we have to find the element and then we have to delete it. And if we want to actually remove the element, then we have to close that gap, and that does take a while. And finally, it is a fixed size. So if we try to add more stuff, we have to do some fancy tricks in order to actually increase the full size of the array, but normally we're limited to the fixed size. A variation of the array is what we call the ordered array, or a sorted array. This is the same thing as our typical array in structure. The only difference is that we require all the elements to be sorted in some order, whether it's an increasing order or decreasing order. And what's nice about this particular array is searching is a lot faster. So since the array elements are sorted, we can take advantage of some new algorithms that speed up how long it takes to find a specific element. But there are still several downsides to the ordered array. Some of them are almost identical to that of the typical unsorted array. But one disadvantage is that inserting is slower. We can't just insert an element wherever we want now. So we have to find where it would fit correctly in here, because we must maintain this sorted order. So we have to find the right spot and then shove all the elements. So adding something to the array is a lot slower. Deletion is slower, and it's just as slow as with an unsorted array, because we have to find the element we want to delete, take it out, and if we need to, shove all the elements in. So that does take some time. And then just like with unsorted arrays, we still have that fixed size limitation. The next data structure is what we call a stack. Now, we will talk about what this data structure is later on in the course. But what's nice about this type of data structure, it uses what's called a last in, first out access. So what that means is we add stuff to this stack, and the last thing that's added is the first thing that we are able to access. So it's very efficient as far as looking at the last thing that was added to this data structure. But the problem with this data structure is accessing items in general is pretty slow. So while the last item we can find very quickly, if there's something buried in the data structure, we kind of have to go through quite a few elements in order to find that item. So we do have slow access in general. Another data structure we're going to take a look at is what's called the queue. And what's nice about this approach is that it's similar to the stack, but it uses a first in, first out access. So we add stuff into this queue in some order, and the first thing that's added is the first thing that gets accessed. So we can add stuff, then we can access stuff very quickly. It's a really nice approach with it. But for any arbitrary element, accessing it is going to take a while. So let's say we want to access the last thing that was added to the queue. Well, we have to go through all the other elements of the queue first before we can get to that last element. So accessing items here could also be very slow. Another data structure that we'll look at in this class is what's called the linked list. And it's kind of like an array, except they're not all grouped up together. So what's nice about this particular data structure is that inserting an element is actually very quick. We can put it in wherever we want, and we don't have to shove any elements. And then deleting is also very quick, because what we'll find with this is if we need to remove an element from here, we can tie the data structure together very easily without shoving any elements. So adding and removing elements in this data structure is very quick. But the big downside with this data structure is that searching is very slow. What we'll see here is we don't have an index for the elements in this data structure. So we're not going to be able to directly find or directly access or find a particular element. We have to search through the whole thing in order to find what we're looking for. We're now starting to get into some of the data structures that we won't see in this class, but I do believe it's worth mentioning that they exist, and then you'll see them in other classes. So the first one is what we call a binary tree. And just to kind of give you an overview of what this data structure does is, imagine we have some element, and that element is connected to two other elements, or at least up to two other elements. And then each of those elements are connected to two other elements and so forth. So one way to describe this, let me see if I can try to illustrate this over here. So we have some elements. I'm going to use circles for elements. So we have an element here, and then maybe this is connected to two other elements like this. So here are two more elements. And then maybe this element is connected to two more elements like this. Maybe this one's connected to only one more element. So this is what we call a binary tree, because each element is connected to at most two more elements on the lower level. So that's what we mean by binary tree. And what's nice about this particular data structure is that searching is very quick, inserting is very quick, and if the tree is what we call balanced, and what we mean by that is you don't have something like a whole string of elements all down one branch of this tree, but it's kind of like each level of the tree has a balanced number of elements in here. Deleting is also very quick. So we can search stuff, insert stuff, and delete stuff in here very quickly with this particular data structure. But the big disadvantage with this is deleting can be very complex. Like in this particular example, let's say I delete the element right here, this one. So what happens to the two elements underneath it? So we need to move one up. So that gets a little bit tricky. So that's the one downside to binary trees. Another type of tree-like data structure is what we call the red-black tree. So the binary tree, we saw that we had like one element and they were connected to two other elements and so forth. So that's this tree structure. So the red-black tree is that type of tree-like structure. It's not necessarily the case that each element is connected to at most two others, but each element is colored red or black. And what you would see later on is that there are some different things that we can do with red-black trees. So what's nice about this is similar to the binary tree is that searching, inserting, and deleting are all very efficient. And what's also nice about this particular data structure is that we require that the tree is balanced. So we have all these elements on the appropriate levels. There's not like one, like as I mentioned before, the binary trees, you don't have like this one element that's connected to one element, that one's connected to one element, that one's connected to one element. That's what we call an unbalanced tree. But these types of trees are balanced. The problem with this particular data structure, though, is that it's a very complex data structure. And that's why we're not going to talk about it in this class. We're going to save that for the data structures course. Another variation of the tree data structure is what we call the 2-3-4 tree. Now, the way this works, at least giving a very brief explanation of it, is that the elements in this tree either have 2, 3, or 4 elements connected to it. There's some other terms with children, so we can say that an element has 2, 3, or 4 children. And based on the number of children, the number of elements attached to it, there could be some different types of number of elements altogether. That's probably the best way of describing without going into a lot of details. But what's nice about this, just like the other trees that we talked about, searching is very quick, inserting is very quick, deleting is very quick, and this is also another tree that's required to be balanced. And this particular type of tree is really great for disk storage. So as far as algorithms for storing stuff on a disk, this type of tree data structure is a very common data structure that's used for managing how things are stored on a disk. The problem with this data structure, as you can probably guess, is it's a very, very complex data structure, far more complicated than the red-black tree. Another popular data structure is what we call the hash table. Now, let me give a very high-level explanation of this. So let's say we have some data structure and we want to add or access elements of this. We're usually given some type of key. Think of it kind of like a formula is a way you can kind of think of this key, where if we want to access something or insert something, we would take the item that we want to search for or insert, combine it with this key, do some computation magic stuff behind the scenes. It gives us some number, and that tells us where to put it or where to look in the data structure. That's pretty much what's going on here. So what's nice about this is if we know what this key is, accessing the data structure is very efficient because we just do the computation and it tells us exactly where to go in the data structure. And then inserting is very quick because we take the key, then we just do the computation, and then we insert stuff. There are some problems with this data structure though. One of them is that deleting is very slow. So if we are trying to find something to delete, we have to search for it. So we have to use the key to find it, and then we have to delete it, and then we might have to do some additional stuff after something is removed, depending on how the data structure is organized. If we don't know the key, then accessing is going to be very slow because we can't just directly access the element we want. We're going to have to look through everything if we want to search for something. And another issue is this is not a very efficient data structure in terms of memory. We actually allocate a lot more space than is necessary for this particular data structure. The next data structure we're going to take a look at is what's called a heap. Sometimes this is also what's called a priority queue. And the idea with this is we have this data structure that's set up where either the largest item or the smallest item, depending on how your priority is set up, is accessed very quickly. So this could be set up using an ordered array, or it could be structured using a tree. But the idea with the heap is we have this data structure and it's organized in some way where the largest or smallest item can be accessed really quickly. So what's nice about this particular data structure is that inserting something is very efficient. Deleting an element in here is actually very quick as well. And then of course, as we mentioned, if we're looking for the largest item or whatever the top priority is, that accessing that is very quick. If our priority is dealing with small items, so the smallest item, then accessing that is very efficient. So it just depends on what our priority is for this. The problem with this particular data structure is, although finding the largest or smallest item is very efficient, accessing any other element in this data structure is very slow. The last data structure we'll mention here is what's called a graph. Now, a graph is very similar to a tree. The only difference is elements can actually be connected in what we call a cycle. So I'll draw a very simple example over here. So maybe I have an element here, and maybe this is connected to an element over here, and then maybe it's also connected to a different element over here, and then maybe I have another element over here, and both of these elements are connected to that element. So maybe we have something like this. So this is not a tree because we have this kind of circle. We can go in a circular rotation. So this is called a cycle here. Trees don't have cycles. So this is not a tree, but this is what we call a graph. And this is a very popular data structure. And the reason behind it is because it models several real-world situations. So like, for example, let's say you're trying to use a GPS to find the shortest distance from one city to travel somewhere else. But we can model that problem as a graph where each city would be one of these elements, and then the roads that we would take would be the way we would connect to those different elements. So we can model several problems using a graph. The problem with this data structure is that some of the algorithms for doing stuff with graphs are very slow and complex. Now, the graph itself we'll talk a little bit about in the data structures course, but we use this a lot in the algorithms class, our CS221 course, where there's a ton of different types of problems with graphs and a ton of different algorithms of varying running times or varying times it takes to complete the algorithms. So we'll talk more about graphs in those classes.